All right, welcome back, everybody. Today we're going to talk about lesson number 41. We're first going to review the right triangle trig that we did before break from lesson 40, and then we're going to go ahead and move on to some new stuff, which is solving oblique triangles. And hopefully you remember from your geometry days that an oblique triangle, by definition, means it's not right. We talked a little bit about trig before the break, had a little bit of a survey. I would say that the stuff today you probably remember from geometry, whereas the stuff tomorrow is most likely going to be brand new. So just something to keep in mind as we approach these lessons. So again, to kind of review what we talked about in lesson 40, we have, of course, the two special right triangles. We have the 30, 60, 90 triangle, and then we have the 45, 45, 90 triangle. Just something to kind of be mindful of here. These triangles are often rotated when you see them in different problems. So make sure that you know that the ratios always hold, but you have to make sure that you're looking at the correct angles. So in the 30, 60, 90, across from the 30 will always be the starting length, the length of the shorter side, which we'll call A. Then across from the 60 is always going to be whatever the length of the shorter leg A is times the square root of 3. And then finally, the longest side will always be the hypotenuse. That will always be across from the 90, and that will always be equal to the length of twice the shorter side. And those ratios, again, are true no matter how you rotate that triangle. When it comes to the 45, 45, 90, across from each of the 45s is going to be the smaller side length of A. And then across from the 90 is always going to be the hypotenuse, the longest side, which would be A times the square root of 2. Over here in the top right here, we have a review for you of the three different side lengths of the triangle. Remember that across from the 90 is always the hypotenuse. Then depending on where you label the angle, that's a theta in case I haven't mentioned that before. And again, that's the angle measurement variable that they typically use. So once you decide what angle you're looking at, whether it's the angle at the top or the angle at the right, across from the angle that you choose, that's always going to be the opposite. And then the touching the angle that you choose, that's always going to be the adjacent. So again, you always assign the hypotenuse first across from the 90, and then you assign the other two sides based on their location relative to the theta. We talked about SOHCAHTOA, which remember is just a memory device for how you remember the sine, the cosine, and the tangent ratios. Then, which may or may not have been new, we have three new ratios, the cosecant, the secant, and the cotangent. Remember that these three ratios are called the reciprocal ratios, which means it's just the original three inverted. And not only can you just invert the entire ratio, but you can also write the cosecant as 1 over sine, the secant as 1 over cosine, and the cotangent as 1 over tangent. So then before break, we also saw some applications of these. So let's just go ahead and remind ourselves. So if you have your calculator should hopefully still be in degree mode from prior to break. But if you want to double check, remember top leftish, if you press the mode key, the fourth option down, you should be in degree mode. So in the first box here, we're going to go ahead and find x. So if we're trying to find x, and we have angle 28, we have to decide which of the big three, SOHCAH or TOA, are we going to go ahead and use. So based on where the 28 is, we would say that the 12 is the opposite, where the x is the adjacent. So which of the big six uses the opposite and the adjacent? That would, of course, be the tangent. So the tangent of 28 is equal to the opposite 12 over the adjacent x. You would then go ahead and start by cross multiplying. So you would get x times the tangent of 28 would be equal to 12, which means that x would be equal to 12 divided by the tangent of 28. And then here's where you're going to need your calculators. So very carefully, using parentheses as needed and making sure you're in degree mode, you're going to go ahead and calculate 12 divided by the tangent of 28. And you should, in fact, get an answer of 22.569. And again, we are always going to round to 3 decimal places unless the problem asks you to do otherwise. In the middle box here, you're still being asked to find x, but this time x is a degree measurement. So again, based on where the x is, you're going to go ahead and label the other sides accordingly. So based on where that x is, you would say that the 109 is, of course, the adjacent. And then across from the 90 always has to be the hypotenuse. So which of the big three uses adjacent and hypotenuse? That would, of course, be a cosine. So you would say the cosine of the angle x would be equal to 109 over 134. Hopefully you remember that if you're trying to find a missing angle, you have to get rid of whatever the trig function is, which in this case is a cosine. The way that you would get rid of a cosine is by taking the inverse cosine. If you take the inverse cosine of the left, you're just left with x. If you take the inverse cosine of the right, and of course that means to the -1, you're going to get the inverse cosine of 109 over 134. And again, to bring up the inverse, you're going to press the second, and then whichever trig function you're using, in this case cosine. If you go ahead and do that calculation, you are going to get 35.567 degrees. Again, 3 decimal places unless otherwise noted. And then finally, we didn't talk about this before break, but of course you remember the area of a right triangle, hopefully, of course, is 1/2 the base times the height. That would mean that in this problem here, you're doing 1/2 the base, which is 9, times the height, which is 4. That really equates to be half of 36, which is 18. Remember that whenever you're doing area, it's square units, but in this case, we know it's meters. So we're going to go ahead and say that it's a nice even 18 meters squared. So technically, that reviews everything that we did in lesson 40 before break. We're going to kind of take those things that are true about right triangles, and now we're going to go ahead and extend them to oblique triangles, which again, by definition, means not right. And we're going to start by talking about the area of an oblique triangle. So consider the triangle that's pictured below to answer the following. So again, here's our oblique triangle, ABC. Remember that we're going to say that the angle measurements are denoted with uppercase letters, and then across from angle B would be side B, across from angle A would be side A, and across from angle C would be side C. And then if we're looking at triangle ABC, this is of course an oblique triangle, and then notice I decided to drop a perpendicular. So when I dropped that perpendicular, it made a right angle, and we're going to go ahead and call that the height of the triangle. So just as we mentioned earlier, from geometry, what is the area of any triangle? Well, that's of course 1/2 base times height. And then if we're looking, we're usually used to using that for a right triangle, but technically it does work in all instances. So in this case, if we're talking about the area of this triangle, it would be 1/2. The length of the base in this case would be A, and then the height would be H. So 1/2 base times height is a great formula. It does work for any kind of triangle, but it's not often that you're going to know the height. So instead of having to do that extra step every time of finding the height, what we're really trying to do here is kind of find a shortcut. How can we find the area of any triangle if we don't actually know what the height is? So in order to help us do that, we're going to rewrite the formula using trig ratios. So we need some sine, some cosine, or some tangent. They give us a couple of values here. They tell us that the length of B is equal to 9. So I'm going to go ahead and add in that measurement. Then they tell us that the side A is going to be equal to 17. And then they tell us that the measure of angle C is going to be 67 degrees. So I'm going to go ahead and add all of that in. If you are looking at the right triangle over here on the left-hand side, based on the information that's given, what is the variable that I don't know? What is the unknown? So that would be H. We're going to go ahead now and try to set up some trig function to find the variable. So based on what we know here, if I know 67 and I'm trying to find H and I know 9, that would be an opposite and a hypotenuse. So I'm going to go ahead and say that the sine of 67 is equal to H over 9. Then I'm going to go ahead and cross multiply, which means that H is going to be equal to 9 times the sine of 67 degrees. Now that I know that H is equal to 9 times the sine of 67, I'm going to go ahead and substitute that in to the H in the area formula. So the area of this triangle is going to be equal to 1/2 times the length of A, which is 17, times 9 sine of 67. And again, if I carefully plug that into my calculator, I'm going to get 70.419. And I don't know the units, so I'm just going to say square units or units squared. You really should write something just to denote that you do know that they are, in fact, square units. So notice that in this case, I ultimately found the exact value of the area of the triangle, but I never actually found the value of H. I just found it in terms of a ratio, and that's going to go ahead and allow me to find a brand new formula. So if I look at what I did there, And I want to now find an alternative formula for the area of a triangle if we are given two sides of the triangle and the angle between them. So just to show why that works, again, if you go back to the picture, 17 and 19, that means I have these two sides of the triangle, and then I have the angle between them, which would be 67. So that's the only time for which this is actually going to work. So the formula is going to say that the area is going to be equal 1/2 times, we'll say, the product of two consecutive sides, and they have to be in a row, times the sine of the angle between them. And again, that is always going to be the case here. If you're given two sides of a triangle and then the angle between them, you're allowed to use the following area formula. So if we take those words, 1/2, the product of two consecutive sides, times the sine of the angle between them, we're actually going to come up with three formulas that you could use for any triangle ABC. So if you're trying to use triangle ABC, you could say 1/2 A times C times the sine of B. Based on the position of the variables, big B will always be the angle between side A and side C, which would, of course, then give us a second version, which would be 1/2 AB, and then times the sine of C, which would then ultimately give us the third version, so 1/2 BC times the sine of A. So again, let's just be clear what it is we found here. What we just did is we developed a formula for how to find the area of any triangle for which you know the lengths of two consecutive sides and the angle between them. So that's going to be very, very handy. The only thing I would caution you on, this is strictly an area formula. You're only going to use it when it asks you for the area. If it asks you for anything else, this formula doesn't apply. So now that we've talked about how to find the area of any triangle, we're going to go ahead and talk about how you would solve any oblique triangle. Remember that SOHCAHTOA only works if you have a right triangle. We're going to be talking about oblique triangles, which are triangles A, B, and C. Now, of course, you can always drop a perpendicular to find the height of the triangle, but that's always going to be extra work. The whole point of what we're going to do now is try to find some formula, some way around that, so we don't have to do that every time. So use the picture that's given and find the following. So using angle C, find an expression for H in terms of B. So if we're going to go ahead and do that, we're going to be looking here at this triangle, and we're going to be trying to find angle C and find an expression for H in terms of B. So that means that we're going to want to go ahead and connect C, B, and H. So again, the way that we would do that is by using the sign. So we can say that the sine of C would be equal to H over B. We want to go ahead and solve it for H equal. So H is equal to B sine C. Let's keep that in our back pocket and just make sure that looks like a C, not an E. Okay, so now we're going to go ahead and use angle B, and we're going to find an expression for H in terms of C. So now we're going to go ahead and look over here. So again, if we're trying to use angle B, H, and C, that's going to be another sine. So we can say that the sine of B is equal to H over C. If we go ahead and solve for H again, we can conclude that H is equal to C times the sine of B. Keep that in our back pocket. And now take a look at the final column here. If the previous expressions are both equal to H, which of course they are, then what can be concluded about the two expressions themselves? Well, hopefully you can conclude that they have to be equal. So we're going to go ahead and set them equal to each other. So that would mean that we could say that B sine of C is equal to C sine of B. So while that's true, there's actually a nicer way to do that. So what we're going to do first is we're going to divide both sides by B, and we're also going to divide both sides by C. If we do that, then the B's will cancel out on the left side, and the C's will cancel out on the right side, which is going to leave us with the expression that the sine of C over C is equal to the sine of B over B. And it turns out that that's kind of what we're hoping for. This leads us to something called the law of sines, which again, maybe you have heard of before, or maybe not. The law of sines will always work if you are talking about the relationship of the sine of an angle and the side across from that angle. So to kind of formalize that, so in an oblique triangle ABC, the following ratios are equivalent. So you can say that the sine of A over A is equal to the sine of B over B is equal to the sine of C over C, and that is the law of sines. Now, a couple of things that I want to point out about the law of sines. So one, you're only ever going to use two of the ratios at one time. So either sine of A over A equals sine of B over B and then solve, or use B and C. You're not going to ever use all three at the same time. You're only ever going to use two. Secondly, not only is this version of the law of sines true, but it also would be true if you inverted everything. So sometimes you see the side lengths on the top and then you see the sines on the bottom. That's equally true. So it doesn't matter which version you use. So how is that going to help us here? Well, this is now going to allow us to solve any triangle as long as we have the proper information. So let's take a look at this next example. They tell us about some of the side lengths. We're going to solve the triangle, which again means find all the missing sides and all the missing angles. And we're going to go ahead and round to 3 decimal places each time. So definitely a good idea to go ahead and draw an oblique triangle, then label it ABC. Doesn't matter where you put the A, the B, and the C. When we get to the book, it will tell you the orientation it wants you to draw it. Otherwise, it doesn't matter as long as you have the appropriate little side. So little A, little B, and little C. They're telling you that the measure of angle B is 130 degrees. So that actually should look, obtuse, but it's okay if they're not necessarily drawn to scale. We know that C is equal to 11 centimeters, and we know that B is equal to 15 centimeters. So lots of good information here. Again, notice that we're not going to use SOHCAHTOA because there are no right angles. Yes, you could drop a perpendicular and then solve for H, but the whole reason why we found the law of sines is now we don't actually have to do that. So looking at the information that's given, using the law of sines, there's actually only one thing we're going to be able to go ahead and solve for. So if you have a matching side length and the angle across from it, and then you know that C is equal to 11, the only thing you're going to be able to find from the start is the measurement of angle C. So in order to do that, we're going to use the law of sines, which says the sine of some angle divided by the side length across from it is equal to another angle divided by the side length across from it. Now, here's where you have to be careful with your calculator. You're not going to use your calculator until the very last step. So go ahead and cross multiply. 11 sine of 130 is equal to 15 sine of C. Then to get the sine of C by itself, you're going to divide. So the sine of C is equal to 11 sine of 130 divided by 15. Only once you have reached this point can you use the calculator. Don't round anything along the way. So to get the C by itself, hopefully you remember that you're going to have to do the inverse sine of this entire expression. So 11 sine of 130 divided by 15. So you have to be really, really careful every time you're doing these kinds of problems using the calculator. So you're going to hit your second sine. You're going to do 11 sine of 130 divided by 15, and your calculator will actually be okay by just following those order of operations. So you can kind of just plug it in exactly like that, and that'll give you the measurement of angle C, which in this case is equal to 34.178 degrees. So that is angle C. Oops. So now that I have two angles, I can, of course, find the third angle by just using some common sense. So if I want to find angle A, I'm going to take 180 degrees. I'm going to subtract 130, and I'm going to subtract 34.178. I got rid of that by mistake. So 34.178. So I'm going to subtract 34.178. And if I do that very carefully, the measure of angle A is going to be equal to exactly 15.822 degrees. Oops. Sorry about that. There we go. All right. So now that I have all that information, the last thing that I need to go ahead and find is the length of side A. Luckily for me, now that I know what angle A is, I'm going to go ahead and solve. I would always recommend that you use the original information. So the fact that you already knew 130 and 15, I would just recommend using those as opposed to using the C values, just in case you made a mistake along the way. You don't want to now make a second mistake. So from here, I'm going to go ahead and set up a second ratio. So I'm going to say that the sine of 130 over 15 is going to be equal to the sine, sorry, I should put a little meter for you there, is going to be equal to the sine of 5.822 over A. Cross multiply and divide, and you're going to get A is equal to 15 times the sine of 15.822 divided by the sine of 130. In this case, because you're just looking for a missing side length, you don't have to do an inverse anything. You just have to very carefully plug that in your calculator, and you're going to get 5.339. And because we knew it was centimeters, you can go ahead and label it as such. Try not to get sloppy with your units. I know it's hard. You don't want to test or quiz. Make sure you don't forget it on the homework. It's not that big of a deal. Oh. So you are, of course, trying to solve this oblique triangle, which means you're trying to find all the missing sides and all the missing angles, which I've done. As a quick little check when you're done, you can always just confirm that the largest side length should be across from the largest angle. The smallest side length should be across from the smallest angle, and the middle should be in the middle. So the law of sines is great. It's fantastic. We love it, but it doesn't work all the time. So in order to apply the law of sines, what combination of information do we have to know? So it turns out that in order to use the law of sines, we have to know an angle and the side across from that angle. So an angle and the side So that's what we have to know in order for the law of sines to work. Just so that you're aware, the things that would make that true would be things like angle, side, angle, side, angle, and side, angle. What combinations would not allow you to use the law of sines? Well, that would be side, side, angle, side, and then angle, angle. Hopefully, you remember those abbreviations back from geometry. So generally speaking, you're going to use the law of sines when you have more angles than sides, of course, except for choice number 3. And you're going to use the law of cosines when you have more sides than angles. Careful to note here about angle. If you remember back from your geometry days, you can actually never use just the angles. That is going to give you a similar triangle. It's not actually going to allow you to have, congruent stuff. So that will not be used ever. But basically, if the law of sines does not work, you're going to have to use something called the law of cosines. So the law of cosines, again, takes several different forms depending on which values you're given. So if you're trying to find a missing side length, so a squared would be equal to b squared plus c squared minus 2 times b times c times the cosine of the angle that matches, which would be A. Then you can also say that b squared is equal to a squared plus c squared minus 2 times ac times the cosine of b. Then you can say that c squared is equal to a squared plus b squared minus 2ab times the cosine of c. So give you a second to write all that down, and a couple things you want to watch out for. Now, I didn't actually show you this proof, although I could if you want to see it, but I have a feeling you'll take my word for it. Notice that because it's the law of cosines, you're obviously using the cosines all the time. And again, for the angles, notice that if you're solving side A, you're going to do the cosine of A. If you're solving for side B, you're going to do the cosine of B. And if you're solving for side C, you're going to do the cosine of C. So just to make sure. Notice also that for the other variables, whatever variables you're squaring on the right-hand side, those are going to be the same ones that you're multiplying times the cosine of A. So again, just be careful. All right, and look at that, like magic, you now see a whole bunch of other stuff written. I wanted to pause and make sure that I wrote it so I didn't make any mistakes. Just like when we talked about law of sines a few minutes ago, and I told you that you could invert the top and bottom and get an equivalent expression. Turns out that you can take each of those three versions of the law of cosines, each of which isolates the side length, and you can just rewrite them so that the angle measurement is isolated. So go ahead and copy these three new versions while I go ahead and just kind of talk about them. Notice that for each of them, you now have isolated the cosine of the variable, and instead you now have a fractional expression on the right hand side using all of the different side lengths. So again, take a minute to just kind of jot those down. I promise you that all technically 6 versions will work. It's really just a matter at a certain point as making sure that you can plug the appropriate version into the calculator. So now to kind of finish up, our ultimate goal after what we just talked about for the last 20 minutes is for you to be able to solve any kind of triangle, whether it's right or oblique. Just to be clear, in the future, if you do go back to seeing just those easy right triangles, continue to use SOHCAHTOA, obviously because those are easier, and then only use the law of sines or cosines when you have an oblique triangle and when you have the appropriate angles and side lengths. So take a look here at the one on the left. I drew a little oblique triangle there, ABC, and then I put in all my measurements. So notice that based on the information that was given to me, what I have here is a side situation. And when you have a side situation, if you go ahead and look up at the top, that means you're going to go ahead and start by using the law of cosines. So from here, because of the fact that I know all 3 of the sides, I technically could find any of the angles to start. So I'll just go ahead and go alphabetically. So if I'm going to try to solve for angle A, I'm going to go ahead and use the version of the formula that has the A's isolated. So I'm going to go ahead and say that A squared is equal to B squared plus C squared minus 2 times B times C times the cosine of A. Just like I mentioned a few minutes ago, you need to be very careful in the calculator. You don't want to actually round anything until the very last step. So not rounding means you still can calculate things that are nice. So 36 is going to be equal to 4 squared is 16 plus 81, that's 97, minus 72 times the cosine of A. Subtract the 97, you get negative 61 equals negative 72 cosine of A. You're going to go ahead and divide. So the cosine of A is going to be equal to 61 over 72. And again, don't, round anything. Don't actually calculate that. Only now when you actually go ahead and solve for angle A, and hopefully you remember you need the inverse cosine to do that. So you're going to do the inverse cosine of 61 over 72. If you go ahead and do that very carefully, that is the first value that we're looking for, which is angle A is equal to 32.089 degrees. Then notice from here, we need to go ahead and solve for a second angle. So let me change colors and let's go ahead and solve for angle B. So in this case, we're going to use the B value on this side. So 4 squared is going to be equal to the other 2 sides squared. So 6 squared plus 9 squared minus 2 times those 2 sides, and then cosine of B. So 16 is going to be equal to, that's 36 plus 81. So 36 plus 81 is 117 minus 108 cosine of B. 16 minus 117 is negative 101 equals negative 108 cosine of B. So the cosine of B is going to be equal to positive 101 over 108. You're going to go ahead and do the inverse cosine of that value, which is 101 over 108. And again, if you do that nice and carefully, you're going to get 20.742 degrees. And then all that hard work to find angle A and find angle B, you can go ahead and take a little vacation for angle C. You're going to go ahead and do 180 minus 32.089 minus 20.742. And that is going to give you the third angle of 127.169 degrees. Go ahead and highlight those for you. So A, B, and C. Again, the reason why we had to use the law of cosines to start was because it was side, side, side. You can't use the law of sines if you don't have any angles. Again, my recommendation is when you finish a problem like this, just go ahead and take a quick minute to make sure that everything makes sense, meaning that the largest side is across from the largest angle, check. The smallest side is across from the smallest angle, and then the one in the middle should hopefully be in the middle. So one last problem here. Here we're given A is 12, C is 7, and B is 65. So if I go ahead and add those values in, you can see that you have a side, then you have the angle between them, and then you have another side. So again, if it's a side angle side, that's how you know you're starting with the law of cosines. If you're going to go ahead and start with the law of cosines, over on the left side, we could have solved for any of the angles. Here, there's only one thing that we're going to be able to find, and that's going to be side B. That's the only expression that we're going to have enough information to go for. So B squared is going to be equal to the other two sides squared being added minus 2 times those sides being multiplied times the cosine of the angle that matches. And then again, you are just going to, I think the easiest thing you can do in this case is just plug that into your calculator exactly as it appears. So the square root of 12 squared plus 7 squared minus 2 times 12 times 7 times the cosine of 65. I know it kind of seemed like that is messy, but the truth is there really isn't anything crazy going on there. So if you plug it in exactly as it appears, which again, you should be following along hopefully with your calculator as I do mine, you should go ahead and be able to solve that B is equal to 11.045. So now that we've solved for side B, we still have to find angle A and angle C. Just because we had to start the problem using the law of cosines, you are allowed to switch to the law of sines at some point if it's easier. We actually could have done that in the previous problem as well, but I'm trying to show you all of your options. There is a reason why using the law of cosines is actually safer than using the law of sines. It has to do with what's called the ambiguous case of the law of sines. Again, maybe you remember what that is, side-side angle. We'll talk more about that in the coming days, but for now, I know for a fact that we're safe. So we're going to go ahead and solve for one of the missing angles. And again, let's just go alphabetically. So let's go for angle A. So if we're going to go for angle A and we're going to switch it up to use the law of sines, then we can say that the sine of angle A over the length of side A, which is 12, is going to be equal to the sine of 65 over 11.045, which we just found. If you go ahead and cross multiply and divide, you're going to get that the sine of A is equal to 12 sine of 65 divided by 11.045. And again, in order to actually calculate that, you're going to have to do the inverse sine of that whole expression. So very, very important that you're taking your time and plugging that in precisely. We're definitely focused on quality as opposed to quantity in terms of the problems that I'm going to assign you. So angle A is going to be equal to 79.944 degrees. Highlight those for you. So 79.944 degrees. And again, just like before, now that I have two of the missing angles, I can go ahead and find the third by simply subtracting 180 minus the angles that I know. So minus 65 minus 79.944, which means that the remaining angle C is going to be 35.056 degrees. So I would just caution you again, if you round along the way, even though I told you not to, if you do round along the way, your answer gets farther and farther away from the one that I'm going to get every time you press enter and do a calculation. So if you wind up in your answer keys with answers that are slightly different than mine, it's probably because you were rounding when you shouldn't have been. So again, when at all possible, don't round until the very last step. So after today, hopefully you reviewed how to solve right triangles. You now know how to solve any oblique triangle using the law of sines and cosines respectively. And then you can now find the area of any triangle, whether it's right or not. So thanks very much for tuning in, guys, and we will catch you next time.